Okay, welcome back to the Oz Geometric PD seminar. So our speaker today is Tim Buttsworth, who you should all be familiar with. He's going to speak on scalar curvature along Ebin geodesics.
Cool, thanks very much. Thanks very much for the introduction, Ben. And thanks for everyone to the audience for coming and putting up with the organizer of this seminar deciding that he wanted to give a talk in his own seminar series. So thanks very much. All right, let's make this full screen. I've forgotten how to do this. There we go. I'm blind. Okay, so yes, the topic was scalar curvature along Ebin geodesics. This is work I've been doing with Christoph Bohm and Brian Clark. Christoph Bohm might be familiar to some of you. Brian Clark was a postdoc of Christoph Bohm about a decade ago. He's now in industry, working in mathematical biology, I understand. So this is work they started quite a while ago, left it on the back burner, and they invited me to finish it for them. Perhaps is a bit too strong, but nevertheless, I've gone on board and I'm quite excited about this particular topic, and I'm quite keen to share some of this with you. All right, so the setting is smooth manifolds. I'm going to insist that these manifolds are smooth, and I'm also going to insist that they're closed. So I'll only focus on those that are compact and without boundary. Some of this theory does apply to the non-compact case. It should be fairly, well, hopefully it should be fairly obvious which parts of this work extend to non-compact guys and which do not. Now, usually this isn't just topology. We're interested in geometry, and so that means we tend to put Riemannian metrics on our smooth manifold. So we're going to use mathcal M to denote the set of all Riemannian metrics on M. The key object of interest in this talk is going to be the Einstein-Hilbert functional. So once you have a Riemannian metric on your manifold, you can do geometric things. You can talk about the volume form. You can also talk about various forms of curvature, the Riemann, the Ricci, and perhaps most relevant to us today is the scalar curvature. The Einstein-Hilbert functional is then constructed. It's a function that goes from the set of Riemannian metrics into R. And this function is, you take as input a Riemannian metric, and as output, you take the real number, which is found by integrating the scalar curvature of that metric with respect to the corresponding volume form. So this is actually a fairly well-studied object, both in Riemannian geometry and in general relativity. The Einstein-Hilbert action is quite important to the Einstein theory of relativity. From a pure mathematics perspective, or in the Riemannian setting, the most important, perhaps the most obviously important thing about the Einstein-Hilbert action is that, well, it's a function from something into R, and so you can use calculus of variations to study critical points. It turns out that the critical points of this functional are precisely the Einstein metrics. Everyone loves Einstein metrics. Everyone wants to construct new Einstein metrics. And so this in part explains the interest in the Einstein-Hilbert functional. All right, so this is the main theme. We've got a functional. Want to use the calculus of variations, analytical techniques to find critical points. How do we go about doing that? Well, perhaps when you're studying a function, perhaps the first obvious thing to do is look at the domain of this function. So let's have a look at mathcal M, the set of Riemannian metrics on this manifold M. If we're insisting on smoothness, then it's not easy. Well, I don't think you can turn this set into a Banach manifold. C infinity doesn't quite work with that, but this set is a Frechet manifold. It's an infinite dimensional Frechet manifold. So its tangent spaces are Frechet vector spaces. So that's perhaps something important to note. Perhaps what is more important is the fact that you can actually put a Riemannian structure you can put a Riemannian structure on this infinite dimensional Frechet manifold. So just like with manifolds and Riemannian metrics, where you specify an inner product on the tangent space at each point, you can do the same thing for this infinite dimensional Frechet manifold. There are plenty of choices of metrics that you can put on this space, but seemingly the most popular and natural one to put is the L2 metric on this infinite dimensional manifold. And I think sometimes this is also referred to as the Ebin Riemannian structure. So how do we specify it? Well, an inner product at every tangent space. First, you need to actually pick a point in your infinite dimensional manifold. So let's pick a point in this manifold. To specify an inner product, I have to take two elements of the tangent space. So these are going to be symmetric 0-2 tensor fields. And then the metric is found by taking the inner product of these two symmetric tensor fields and then integrating over M. For those who are unfamiliar, you might not like this expression here because the Riemannian metric, originally it will take inputs as vector fields, but there's a fairly natural way of extending that to an inner product on symmetric 0-2 tensor fields. Okay, now perhaps the main important reason why this Riemannian structure is so good is because, well, like with other Riemannian metrics, you can ask about geodesics. This metric is so nice because the geodesics, you can basically write them down very explicitly. The geodesics are, well, relatively well understood. So what you do, let's say you're interested in a geodesic starting at a particular Riemannian metric G, and you're interested in shooting this geodesic in a particular direction H. So H is going to be a symmetric 0-2 tensor field. Then the geodesic that starts at this point and going in this direction is explicitly solvable. It's this expression here. So gamma T, this is a one parameter family of Riemannian metrics. What you do, since it's a family of Riemannian metrics, you have to specify what it's doing for two inputs. What it's doing is it's taking the first input and applying an endomorphism to it. The second input is left alone. Now, this endomorphism is the exponential of T times capital H, where capital H is basically the raised indices version of small h. So it's related to small h via this equation here. So this is quite exciting. We know what the geodesics are. All right, so let's take these geodesics and try and apply them to the study of the Einstein-Hilbert functional. Basically, since it turns out that all Riemannian metrics have this form, well, any Riemannian metric is, you can find a geodesic that joins any two Riemannian metrics, I think. And so that means that it suffices to study the Einstein-Hilbert functional by assuming that your metrics have this particular form. So we look at metrics that look like this. So why is this useful to do? Well, I think I forgot to mention this earlier, but when you use the calculus of variations to find critical points of the Einstein-Hilbert functional in order to find Einstein metrics, you need to insist on the volume 1 constraint. I might have forgotten to mention that, because with the volume 1 constraint, you basically end up using, well, it's Lagrangian multipliers, which is why you get that lambda out the front of Ricci G equals lambda G. So we're mostly interested in studying the Einstein-Hilbert functional on volume 1 metrics. This is quite nice if we're looking at metrics of this form, because the volume 1 constraint is actually going to turn into a linear constraint. So this metric gamma T is going to have volume 1 if and only if the original G has volume 1 and if the integral of the trace of H taken with respect to the volume form is 0. This is very nice. This is a linear constraint, and since it's a linear constraint, that means that the set of metrics with volume 1 is actually a totally geodesic submanifold of this set of Riemannian metrics. So, well, that's surely exciting when that happens. Now, what I find very, very exciting is that you don't actually have to stop here. So there's a result that goes back to Moser in the 60s, which basically says that in addition to assuming that trace of H equals 0 in the integral sense, you can actually assume that trace of H is equal to 0 uniformly. And the reason is that you can always prescribe the volume form of a Riemannian metric. So what do I mean by that? Well, a quasi-precise statement is as follows. If M is connected and compact, then if you pick any two Riemannian metrics G1 and G2 on your manifold, it's possible to scale one of them and apply a diffeomorphism to one of them, so that the diffeomorphism going from M back to itself, it's possible to find both a scale and a diffeomorphism so that the first metric has the same volume form as the second metric. So, well, this is quite nice because if you pick a reference metric to start your geodesics at, then for any other metric, you can find a diffeomorphism and a scale so that it has the exact same volume form as what you started with. So because this is the Einstein-Hilbert functional is a very geometric object, it makes sense to make attempts to, in some sense, quotient out by the diffeomorphism group. That quotienting out by the diffeomorphism group is basically a nonsense statement. It's too hard to do that. But I interpret this theorem as providing a sort of a partial quotient by the diffeomorphism group. So the upshot of this is that since this is geometric, in addition to, without loss of generality, assuming that volume is 1, we can actually assume that trace of H is equal to 0 everywhere, and that all of the Riemannian metrics we deal with, they all have the same volume form, the same volume form that you started off with. So the upshot of all of this is that we have the ability to, well, in a sense, we're now able to reduce the complexity of what we're studying. So we're interested in the Einstein-Hilbert functional. We take a Riemannian metric, find its scalar curvature, and evaluate against the volume form of that Riemannian metric. But what you can do is pick an initial Riemannian metric G0, look at what its volume form is, mu0, and if you're only going to look at metrics of this form, where H is traceless, that means that, well, dVg is always going to be the same as mu0, and we're just left looking at the scalar curvature of gamma H of t. So one simplification that's obvious is that instead of having to look at the scalar curvature multiplied by the volume form, it now suffices just to look at the scalar curvature itself. So one partial simplification there. Okay, with this in mind, we'll now, these are basically all the things we get for free to start off with. So let's try and make a move towards actually getting a handle on what this scalar curvature functional actually looks like. So as is quite traditional for these sorts of things, you start by imposing symmetries. So let's suppose that we've got a compact Lie group of diffeomorphisms acting smoothly on our compact manifold M. Then what we're going to do is look at Riemannian metrics on M that are invariant. So we'll denote this with math cal G. Now, because the scalar curvature and Ricci curvature and Riemann curvature commute with the pullbacks of diffeomorphisms, one can use that observation to conclude this interesting result, that if you take the Einstein-Hilbert functional, and instead of finding critical points over the whole space, just look for critical points on the restricted set of G-invariant Riemannian metrics that are volume 1, then you still find Einstein metrics, and of course these will necessarily be G-invariant Einstein metrics. So finding critical points of this thing works well with symmetries, I guess, is the main point of that. So what kind of symmetries could we possibly use? Well, perhaps the most simplifying sorts of symmetries you can use are the homogeneous symmetries. So what you're going to do is assume that your Lie group of diffeomorphisms is actually acting transitively on your manifold M, because in that case, well, we say that our manifold is a homogeneous space, and the manifold has a presentation of G mod H, where G is an appropriately chosen isotropy subgroup. So this is pretty good. The transitivity basically implies that this set of G-invariant Riemannian metrics is going to be finite dimensional. So the Einstein-Hilbert functional is basically just a function going from Rn, not quite, Rn with the volume 1 constraint, with the positivity constraint as well, back into R. And the Einstein equation is just a system of algebraic equations. No derivatives really appear. Of course, since this action is transitive, we conclude that because it's algebraic, the scalar curvature is going to be a constant of the whole manifold. So that means that if we restrict to volume 1, the Einstein-Hilbert functional is the same as the scalar curvature functional, which can now be interpreted as the functional because it's constant. So the scalar curvature goes from the finite dimensional set of G invariant Riemannian metrics into R, and we can try and find critical points. So how does one usually do this? Well, this sort of thing has been studied quite extensively in the last couple of decades, going all the way back. Well, I don't actually know how far back this goes. It goes quite far back. A quite popular thing to do is to very much use the symmetries and the compactness to choose your initial Riemannian metric. So since I cleverly insisted that G was going to be compact, that means that I have access to a bi-invariant Riemannian metric Q on this Lie group. So what we're going to do in order to study these homogeneous Ebin geodesics, what we're going to do is take some Lie algebra decompositions. So we take the Lie algebra math frac G of capital G, same for H, and we're going to choose math frac M to be the Q orthogonal complement of H in math frac G. So we basically identify math frac M with the tangent space of our homogeneous space at the identity coset. So if you're not into homogeneous geometry, maybe you don't need to pay too much attention to this, but the point is that the Ebin geodesics take a particularly nice form here. So what goes on is that we take our math frac M and find an ADH invariant, irreducible, and Q orthogonal decomposition of this space into irreducible summons. It's very important to note that this decomposition is not always going to be unique. In fact, I would say it's very rarely unique. So this is important to note. You choose some decomposition, and you choose an L tuple of numbers, VI, L being the number of summons that you have, and then the geodesic, the homogeneous Ebin geodesic, looks like this. So what you can do, this bi-invariant metric on G passes to a homogeneous metric on the homogeneous space. And so clearly, if you set all of these T's being equal to 0, you just get back that same metric. So you are indeed starting in the right place. And then you pick an L tuple of vectors, and you shoot your metrics along in this direction here. Now, important to note, this is actually quite crucial, that the volume 1 constraint in this case translates to this. No, it's not going to do that. Translates to this linear condition here. The sum of di vi is equal to 0, where di happens to be the dimension of the summons you're dealing with. Of course, you can always reparameterize geodesics to make them go at whatever speed you want. And so therefore, you may as well scale so that the sum of all these vi squareds is equal to 1 after pre-multiplying by the dimension. Of course, you can't do this if v is 0 uniformly, but then you're not really studying anything. You're just studying the metric that you started off with. Okay, so this is quite nice. We've got a good handle on what the Ebin geodesics look like. We've got fairly explicit formula for these metrics. Explicit formula for the metrics means we can get explicit formula for the scalar curvature. So again, this might be a bit overwhelming if you've never seen these sorts of things before, so maybe you don't need to pay too much attention, but I'll mention the important things here. Most importantly, we can actually compute the scalar curvature in this case. It has this form. You've got exponentials of e to the tv, and you've got the dimension of the summons here, and you've also got these numbers bi and square bracket ijk. Now, they're a formula that you can use to find out what these numbers are. So bi is the ratio of the killing form of your Lie algebra to Q. Schur's lemma implies that on each irreducible summons, there are always going to be scalar multiples, whatever. The important thing is that for complex Lie algebras, B is going to be negative semi-definite. And so BI is going to be greater than or equal to 0. That's important. But what is really, really important is that this thing is also greater than or equal to 0. It's a sum of squares. So the important thing to observe here is that, well, more or less what I've written here, in order to understand, since the long-term goal is to find critical points of the Einstein-Hilbert functional, usually we do this by studying asymptotics of this thing as t gets quite large. And so the key observation here is that as t gets quite large, the asymptotic behavior of the scalar curvature functional is basically saying, well, all of these terms are positive and all of these terms are positive. These have exponential growth. These have exponential growth. So which ones are going to win? This is the key question we now need to address. It's basically a competition. Potentially exponential growth over here, potentially exponential growth over here. Which one is going to dominate? So what can we do? So new slide, but I just pulled my formula for the scalar curvature over from the previous slide. This is where you might think that the volume 1 constraint is just a bit of a technicality, but it turns out to be quite important when studying these asymptotics, because since the VI numbers are not all 0, but they sum to 0, that means that at least one of these VI terms has to be negative. So at least one of these terms does actually correspond to exponential growth rather than exponential decay. So that we are actually going to get exponential growth here, provided BI is not 0. If you're interested in homogeneous geometry, you might understand what the implications of this being 0 is. Okay, so exponential growth, well, yeah, possibly exponential growth over here. What about over here? Well, these are quite interesting terms. What I'll point out is the following. Let's suppose that you pick the smallest choice of VI. As I said before, that there is at least one negative number. So that means that the smallest one will also be negative. If you find such a K, and then you find a J and an I so that Vj is less than Vi, then, well, what's this term doing? This thing is positive, and this thing is also positive. And so therefore, this is exponential growth, but more importantly, this number is actually bigger than all of the numbers over here. So this exponential growth term is actually going to dominate all of them, provided this term here is non-zero. So remember, it's always greater than or equal to 0, but we have to worry about what happens if ijk is equal to 0. So there are some, well, it's a homogeneous space, and these terms are defined in terms of various homogeneous space things. So you can make a move towards understanding exactly when these things are 0 and understanding when these things are 0. What this study reveals is basically the following. For generically, if you just pick a random choice of ADH invariant decomposition M and a random choice of V, with 100% of the time in the measure theoretic sense, your scalar curvature is going to tend to minus infinity. And there are only a handful of exceptional cases where the scalar curvature does not do that. So this is a pretty important observation. And in fact, this is an observation that Wolfgang Ziller made with Mackenzie Wang quite some time ago. In order to get a really good grip on what's going on here, those two, alongside Christoph, Bohm decided to introduce graph theory into the mix, because why not? So one convenient way to describe the situation here is by associating a graph with the homogeneous space, because it turns out that the vanishing of these terms and the vanishing of the BI terms is somehow related to the existence of intermediate subgroups between H and J. So basically they associate a graph to this homogeneous space where the vertices are these intermediate subgroups and edges join if one is contained in the other. So it's pretty funky stuff. Not something I would have really expected to see in a in a geometric and functional analysis journal paper, but there you go. So they get a pretty good grip on what's going on here. They find directions in which the scalar curvature is going to plus infinity. And as we observed before, most of the time it's going to minus infinity. So, directions going to plus infinity, most directions going to minus infinity. You should be thinking of saddle points. You should be thinking of the mountain pass theorem. And that is indeed what these three authors use to construct new Einstein metrics. So we've got this technical condition here, which I'm not going to explain, but there are some conditions on this homogeneous space that, combined with the graph theory they established, can be used to conclude existence of Einstein metrics with the mountain pass theorem. Now, if you're familiar with the mountain pass theorem, you will know that simply understanding the asymptotics isn't quite good enough. You need some compactness. The precise theorem of the mountain pass theorem requires something called the Palais-Small compactness condition. And so as part of their work, they have to actually demonstrate that Palais-Small compactness holds as well. And they were able to establish this. Another massively surprising thing about this paper is that the techniques that they needed to demonstrate Palais-Small compactness went far beyond homogeneous geometry. They had to use Bishop-Gromov comparison theorem. They had to use the harmonic norms of that Peterson constructed somewhere. They used Cheeger-Colding compactness theory. Meyer's theorem came into it as well. All of these crazy techniques went into establishing that you do actually get enough compactness to justify your use of the mountain pass theorem. Okay, so this was that. Maybe about a year or so ago, Christoph came to me and said, all right, Tim, this is all good, but now I want to do this without any homogeneous symmetry. In fact, no symmetries at all would be nice. And so, well, what can be done without any symmetry? Can we use these sorts of techniques to construct new Einstein metrics? So spoiler, we haven't constructed any new Einstein metrics yet. If we had, I definitely would have led with that. But, we've made some moves towards understanding this theory, and these are some things that I'd like to, I'm quite excited about and I'm happy to talk to you about at the moment. So two key things. In order to use this theory to eventually construct new Einstein metrics, there are essentially two ingredients that you'd need. You'd need a good compactness theory. Palais-Small compactness would be good if you could possibly get it. And the second thing would be to actually understand scalar curvature asymptotics. That seems quite important.
Tim,
now, yeah.
Can I ask you a question?
Yeah.
Oh, okay. I hadn't seen that. Okay, maybe you'll mention. Yes, that was exactly my question. Yes. How do you expect Palais-Small if it doesn't hold in the homogeneity one set?
Yeah.
Forget about it.
Yes, as Ramiro wanted to tell you, I guess I was trying to set the audience up for failure. Could we possibly expect Palais-Small compactness theorem to hold in general? No, shut down. No, you definitely
Good that I didn't spoil it. You pressed enter before I talked.
Yes. Yeah, so spoiler, I mean, well, anyone who's an expert in this will know that, starting in dimension 4 and higher, compactness theory is really quite challenging if you're not going to impose any symmetries at all. In fact, well, over 2 decades ago, Christoph Bohm constructed a sequence of examples of cohomogeneity 1 Einstein metrics, so non-homogeneous Einstein metrics that have, well, Einstein metrics always have constant scalar curvature, and the scalar curvature of this sequence does converge to a positive number. However, the Einstein metrics themselves converge to an Einstein metric which is not smooth. And so what this means is that we've got a sequence of Einstein metrics which demonstrates that the Palais-Small compactness condition cannot hold in general, at least not in its original form. in order to do this, you would need some sort of compactness, but you're going to have to find a workaround for the fact that you don't expect compactness as good as what you have in the homogeneous case.
So Tim, Thales mail in particular would imply that the set of Einstein metrics with, say, a lower bound on the Einstein constant is compact, right?
Yes, that would do that. Yes,
because that would be like a super special case of the Thales mail. I mean, the gradient is just zero.
Yeah, I mean, I guess it depends. It does depend on what topology you're going to put on your domain, of course. So you've got to be a bit careful about what you mean by compactness. Of course.
No, what do you? I mean, C infinity. I mean, just
C infinity. Is that what you want? Yeah, because then you'd need a version of the mountain pass theorem to hold on non. You know, there are heaps of versions of the mountain pass theorem out there. I don't know exactly what. Like the traditional one holds for Hilbert spaces, and then there's a version for metric spaces. I'm not sure how general it goes, but you know, these sorts of things you'd have to keep in mind as well.
Yeah, but I think
it's in the modular space non-compact of Einstein metrics, scalar Einstein metrics. Isn't that something non-compact? You can't expect compactness in general. Einstein metrics.
No, that's what I mean. Clearly, this result by Christoph says that it's non-compact. I mean, but that was my question. If the Thales mail, it just immediately tells you that for lower bound, you get a compact modular space.
It would, yes, it would.
Right. Thanks.
Cool. Yeah. Okay. So
yeah, the other fact is that indicates there's a problem that the critical points have infinite index and co-index. That looks bad.
Yeah. So people who are experts like Wolfgang know that lots of things mess up pretty badly as soon as you start looking into this. And so, well, that means that Christoph and I didn't look at this. This project is not focusing on the compactness theory. We'll leave that for, well, presumably other people who have spent careers looking at compactness results for these sorts of things. But we were quite interested in understanding the scalar curvature asymptotics. So what can you do? What can you say about scalar curvature asymptotics? Well, clearly the first step is to get a handle on a formula for the scalar curvature. Now, of course, you can just go to Wikipedia and see that, oh, there is an explicit formula for the scalar curvature. You write your metric in local coordinates. You take derivatives in the coordinate directions, Christoffel symbols, etc., etc. For us, we found it most convenient to calculate the scalar curvature differently. The way of doing it that we chose was, instead of doing this with coordinates, you do work locally, but instead of taking derivatives in the coordinate direction, you start by choosing a locally defined smooth orthonormal frame. You then calculate the Levi-Civita connection of this locally defined orthonormal frame, and then calculate the Riemann curvature in that orthonormal frame and take traces to get the scalar curvature. So we'll get into that in a second, but just in case you've forgotten, I'll remind you that what's going on here is we're going to fix a Riemannian metric G0, and then we're going to choose, make a choice of H, hopefully as arbitrary as we can. We'll make a choice of H, and we'll start shooting in the Ebin geodesic, which is given by this. And remember, we can assume that H is traceless everywhere, and, well, H is also self-adjoint with respect to G0. Okay, so I've said this is a theorem here. I mean, it's probably a couple of months off, at least, of being on the archive, but I guess I'm quite confident in this at this point, still working some of the details out. But our result is as follows, that if the manifold that you're dealing with is at least 5-dimensional, then there is an open and dense set of choices of traceless H, open and dense with respect to the usual Whitney C infinity topology, so that the limit of the scalar curvature is -infinity, and this is actually uniform convergence on the entirety of M. Now, something to note is that because of the Bohm-Wang-Ziller theory of homogeneous scalar curvature, we know that we can't expect this to hold for all choices of H. The best that you can get in the homogeneous case is open and dense, and this appears to be the best we can do without any symmetries at all. So, that's quite nice. So in particular, since scalar curvature is going to minus infinity uniformly, that means clearly that the Einstein-Hilbert functional is going to go to minus infinity uniformly if you go along in these directions as well. All right, so it's rather technical. Well, I'll try and attempt to give you some idea about what goes into the proof. As I said, the first thing you really need to do is find a formula for the scalar curvature. So remember, we started with the reference G0 metric, and we're going to pick an H. We're going to try and find a formula for the scalar curvature locally around P. Now, the eigenvalues of H and the multiplicities of the eigenvalues of H, these play a very, very important role in this theory. So we take our eigenvalues, lambda1 up to lambda L. Let's suppose that they have the multiplicities M1 up to ML. And I'm also going to assume, without loss of generality, that these eigenvalues appear in ascending order, because this is where our trace equals 0 constraint comes in, because unless all of the lambdas are 0, at least one of them is going to be negative. So that's quite important. It has the same role as what we already saw with the homogeneous scalar curvature. All right, so once you've worked out what the eigenvalues are at the point P, it's convenient to diagonalize H as much as you can.
These are now functions on M, then they're not smooth.
Yeah, that's.
Do you assume that there are no bifurcations, Tim?
No, we don't assume that.
So the sign could change,
So
right?
these are not
Or
smooth
everywhere at every point the same way.
The sign of what could change everywhere?
I mean, the ordering can change from point to point.
Well, yeah, but I'm only dealing locally. So if you've organized your eigenvalues in increasing order at the point P, then you'll be able to find a small enough neighborhood in which that ordering is preserved.
Not if they're multiplicities.
Yeah,
No.
okay, yes,
They're
you're
not
right. Yes,
smooth.
so there are technicalities here. So yeah, you're right. So this could, yeah, sorry, I'm not explaining this particularly well. So it's possible that, so it's possible that these are not, yeah, you're right. This point P could be a bifurcation. So let's just look at the point P by itself. Let's look at the eigenvalues at that point. Now, as you say, you can't expect to smoothly find a local orthonormal frame because of bifurcations. But what you can do, and this is the best you can do, you can ask for a block diagonal form for this thing locally. So you can assume, what I should have said before is that you can assume that the traces of all of these blocks are in ascending order, at least locally. So that's what we're going to do. So I guess I'm really thinking of these lambda1 up to lambda L functions as generalized eigenvalues, maybe is a sensible way of saying it.
I guess you have the freedom to say you only look at H's that do not bifurcate, because maybe that has full measure. I don't know.
Yeah,
Is that what you want?
Yes, but remember, since we're trying to prove this uniformly, that means we are there's no escaping the fact that we are going to have to deal with bifurcations here. So we may as well start with it.
Well, if you have that, then the next problem is that the eigenvectors are not even continuous.
That is definitely
Eigenvalues
true.
are continuous, but the eigenvectors are not.
Yeah, that's very right. So yes, you're right. The eigenvectors are not continuous, but if you relax to this block diagonal form,
Well, that means you find a base of eigenvectors.
Yeah, so you can't. Yeah, so I'll get into some of the details of that a bit later. So at the moment, I'm not trying to find an orthonormal basis for the metric. I'm just trying to find a convenient initial basis for H, and then I'll use that to eventually construct a local orthonormal frame. So yeah, so our starting point is any H. If the eigenvalues have silly multiplicities, then the best we can hope for is this block diagonal form. If all of these multiplicities are equal to 1, then you can actually find a local smooth basis which diagonalizes H in that local thing. But if there are non-trivial multiplicities, then the best you can hope for is this block diagonal thing. So I hope that makes sense and clears up some of the issues. Okay, so yeah, you take this block diagonal form, and then you take the trace out, and you call the trace of each of these the same as these numbers that you started off with. So I've extended these numbers, which were just defined at a point, to smooth functions which are defined in a neighborhood. So this is our starting point. And everyone is very excited about multiplicities, and this is the key thing. How do we actually deal with non-trivial multiplicities? As I said before, lambda 1 you can assume is less than 0 unless you happen to be in the worst case where all of the eigenvalues are 0 at the point P. Okay, so we've got a first basis. This is not an orthonormal basis for our metric yet. This is just a convenient basis for H. In order to turn this into an orthonormal basis for the geodesic gamma H of T, well, we have to take exponentials of square roots of things. So we took a G0 orthonormal basis that made H into this block diagonal form, and we're turning this into a locally defined orthonormal frame for a Riemannian metric. So we now have a locally defined orthonormal frame for our Riemannian metric. The input data was a choice of orthonormal frame G0 orthonormal frame, as well as exponentials of these traceless blocks that we had going down. So once you do that, you can calculate the Levi-Civita connection in this orthonormal basis. You record all of that information with your Christoph symbols, and then the scalar curvature of these things is given by this formula here. Now, this doesn't look especially different from the formula for the scalar curvature that you would see on the Wikipedia page. But because we've gone about defining the Christoph symbols in a slightly different way, this formula for the scalar curvature works a bit better for us. Now, before in the homogeneous case, it was easy to identify terms where you have exponential growth. Moreover, you get exponential growth, which is going to potentially dominate all of the other terms. In this formula, these are the terms here. These terms, I'm not going to do the computation, but you can see that these terms in particular are include sums of squares of these sorts of guys here. And so with a bit of computation, what you can basically do is make the following observation, that provided you have a choice of this thing, which is not 0 in a neighborhood, where I, J, and K lie in appropriate blocks, then you are actually going to get convergence of the scalar curvature to -infinity in that neighborhood of P. So we ask that I is going to be equal to 1. That's because I know that lambda 1 is going to be the most negative eigenvalue, generalized eigenvalue in this neighborhood. And this is good. This is what we need in order to get good convergence. I realize that a lot of the details here I can't possibly include, but this is generally the idea, that I want to make sure that at least one of these special terms is non-zero. Because, well, if you've got enough of these terms, this is the point at which we start allowing ourselves to use the fact that we're only trying to show this is true for an open and dense set. So if my choice of H doesn't actually work, if I've got a choice of H for which all of these are 0 at some point, the question is, can I perturb away from this H in order to get at least one of them to be non-zero? And this turns into the dimension counting part of this proof. If you have at least n+1 of these good terms, whose non-zeroness would imply the convergence we want, if you have at least n+1 of these terms and you're in dimension n, then you can use theory of underdetermined partial differential equations to show that you can generically perturb to get what you want. So the real key question here, and this is the question that is quite related to the issue of multiplicities. Can you insist that there are at least n+1 of these terms? Now, the thing to observe is that having singular multiplicities, so for example, if all of our eigenvalues were 0 at a point, this would be quite traumatizing because, well, I said that 1 has to be equal to I, 1 corresponding to the first block, and I said that j has to be at least as big as that, and k has to be strictly bigger than 1. So that means that there does actually have to be a second block in order to even get these terms. The more blocks I have, the more blocks in this block diagonal decomposition I have, the better. And so that means I really need to worry about what's happening if I've got really singular eigenvalue multiplicities at the point P. So this is when we start turning to dimension counting and we start looking at differential topology. So the key question is, when can I ensure that I've got enough of these terms so that disturbing would get the convergence I need? Okay, so as was pointed out before, things get bad really quickly if you've got eigenvalues of 0, for example, or more generally, if you've got non-trivial multiplicities. Let's suppose that we're dealing with a two-dimensional manifold, and let's suppose that locally, in a local xy coordinate system, h has this expression here. So remember, we're interested in h that is symmetric and traceless. So the origin in this coordinate system, the origin is 0. 2 eigenvalues of 0, the thing is just 0 uniformly. Now, what happens when you try and perturb? Well, you start to understand pretty quickly that no matter what you do to perturb, if your topology is sensible, no matter what you do to perturb, you're never going to be able to remove the existence of a point where h is 0. You can certainly move where this point occurs, but the existence of this point you just can't get rid of. However, this is no longer a problem. This stops being a problem in dimension 3. So in dimension 3, let's do a quick dimension count. The set of symmetric traceless 3x3 matrices is 5-dimensional. 5 is bigger than 3. And so that means it is actually possible to perturb an h with a 0 eigenvalue to completely avoid it having 0 anywhere. So that's good. But so really the main idea behind the proof of this convergence result is doing these sorts of dimension counts for all of the problematic multiplicities. Any multiplicity where I don't get enough terms to generically perturb, I need to somehow assume that they can also be generically perturbed to be avoided. And so the way to do this properly is by observing that the set of symmetric traceless matrices admits a nice stratification according to the multiplicities. And so then the key thing is to observe, is to study this stratification. If you're a differential topology expert, this might be relevant to you. It turns out that this stratification is good. It satisfies the so-called Whitney transversality conditions. And so what that means is that generically, in an open and dense set, we can assume that whenever h encounters a problematic multiplicity, it always does so transversally. And since we've got transversal intersections, that's a statement about the rank of the derivative evaluated at that point. And so lots and lots of dimension counting, what we can eventually conclude, details definitely omitted, starting in dimension 5, we do actually get enough terms. So generically, we can assume we have enough terms, and then one more perturbation, we get the terms that we need. So these are basically the techniques that go into proving this result. So I'm almost done, but I'd like to make a few concluding remarks regarding what's been done and what's known. So just to summarize what we did, we showed that generically, if you start at a Riemannian metric, and go in a traceless direction in your Ebin geodesic, that generically you're going to converge, your scalar curvature is going to converge to minus infinity, and this happens for all compact, connected, closed manifolds of dimension at least 5. Of course, the natural question is what happens in other dimensions? So in dimension 1, of course, there's nothing to study. In dimension 2, there's not really anything to study in regards to the Einstein-Hilbert functional either, and that's because of the Gauss-Bonnet theorem. The Gauss-Bonnet theorem says that the Einstein-Hilbert functional is basically determined by your topology. And so you couldn't possibly hope to expect convergence of the scalar curvature to go uniformly to minus infinity. Okay, well, what about the other dimensions? Dimension 3, what we can show is that it's actually possible to construct choices of metrics for which you cannot perturb away a convergence of your scalar curvature to plus infinity. So there are metrics so that no matter how close you are to that metric, there's going to be at least one point so that the scalar curvature goes to plus infinity at that point. But that's okay if all you're really interested in is the Einstein-Hilbert functional, because the Einstein-Hilbert functional is an integral of this thing. And since the points at which you get this large convergence to plus infinity is so tiny, in the integral sense, the dominating behavior is still you're going to minus infinity. Now, one other remark which might be relevant is that any orientable 3 manifold is parallelizable. And so what that means is that it is actually possible for orientable manifolds, it's possible to find choices of H for which there is a globally defined orthonormal basis. Basically, the tangent bundle is trivial. Christoph refers to this as a topological accident. Somehow God made a mistake when constructing 3 manifolds because he accidentally made all of the orientable ones with trivial tangent bundle. So that's an interesting way of thinking about it. This might just be an aside remark. Exactly how our geometric results relates to the topology is still a bit unclear. Okay, and as usual, dimension 4 is where we're really struggling to work out what's going on. It looks like you do get generic convergence of the Einstein-Hilbert functional to minus infinity, but the formulas that you need to look at in order to understand whether you can expect uniform convergence generically, well, it's pretty complicated. As you can imagine, lots of computation has gone into this project, and maybe this is the point at which we're struggling to find the desire and willingness to do more computations. But that's more or less where we're at the moment. Long term, as I said, it'd be nice to see if this theory could actually be used to construct new Einstein metrics. You can use these sorts of asymptotics to perhaps conclude the existence of Palais-Smale sequences, but of course, since you wouldn't expect Palais-Smale compactness, something bad is going to happen if you try and take the limits. What are limits of these things? Like in the Bohm Einstein metrics, are they going to be Einstein metrics with singularities? Questions that perhaps people with more expertise in compactness theory of Riemannian manifolds are more equipped to answer. All right, I'll leave it there. Thanks very much. Thanks very much for attending.
Thanks, Tim. Okay, does anyone have questions? Ramiro, yeah.
Yeah, Tim, yeah, great talk, thanks. You know, in the homogeneous case, there's a very important aspect is when you don't go to minus infinity, that gives you some kind of rigidity. In this case, will be like some Lie brackets vanishing, and then from that you can deduce, okay, there's some special subgroups, etc. Is there any rigidity expected in the general case when in the non-generic behavior?
Yeah, so I would expect something. Exactly what that is quite unclear at this point. I guess the only thing with
distribution, I don't know, some integrable distribution,
yeah,
some foliation, some. Okay.
Yeah, it would be nice. Again, that starts to head into the topological direction. So something hopefully we'll pursue at some point, but at the moment, yeah, it's all we understand really is what it means locally. And so working out what it means globally might, well, another challenge that hopefully we can get to at some point.
Your perturbations are all local, right?
Yes, and so of course you got to use the compactness, finite cover, etc. Those sorts of arguments go into this as well. Yeah, I guess I forgot to mention that. This is just local. In order to make it global on a compact manifold, you got to patch things together with finite number of perturbations.
So here you're not assuming any symmetry really, but is there some situation sort of intermediate between the homogeneous and the no symmetry at all, the way you could make this work? I mean, does anything useful here come in the cohomogeneity one case, or?
Yeah, we haven't pursued that either. I guess it would be interesting to look at Christoph Bohm's almost explicit examples of Einstein metrics and see how they fit into all of this. Something slightly unsettling about reconciling this with what happens if you do with symmetries is that in both this setting and the cohomogeneity one setting, you would have noticed that we usually do something to partially gauge away the diffeomorphism invariance. In this general case, we use the diffeomorphisms to insist that all of our metrics have the same volume form. In the cohomogeneity one setting, that's usually not what you do. Usually in the cohomogeneity one setting, you use your diffeomorphism invariance to basically reparameterize your orbit space so that it's, well, arc length. So I think that's a slightly different thing to do with the diffeomorphisms than what we do here. So you would have to first reconcile that. So yeah, it would perhaps be interesting to pursue.
So the examples that Christoph produced where you get a limit of things which is non-smooth, is there any advantage in, so here you're working in a space of smooth metrics, but is there any advantage in relaxing that to?
Oh, probably. Yeah, probably.
What do the limits look like? Are they like metric space with, metric, sort of non-manifold examples?
These are the sorts of compactness.
There's conical singularities. They have conical singularities. They're quite nice.
Yeah. Tricky stuff. Yeah. One question that Christoph and I are always arguing about is what is the actual correct topology to put on this space? Not sure we've quite worked that out yet.
On the space of metrics, you mean, or what?
Yeah, on the space of metrics.
It depends on the question, right? Like if you want to take limits, then Gromov-Hausdorff is what you start with, right? But then maybe then from that you can improve regularity if you're lucky.
Yes. Hopefully good things to come. Don't know. I certainly shouldn't discourage any of you from attempting to answer some of these questions.
So in this context, why is it? What's the motivation for looking at only at these Ebin geodesics? Is that natural in this context of the infinite dimensional space or metric?
Well, I guess it's well for me at least, that the fact that they are geodesics with respect to the most natural Riemannian structure is reason enough for me. Yeah, I don't actually think I have much. I don't know if I can say much more than that. What sort of directions do you want to go in?
I don't know. You'd like to have some kind of uniform understanding where it goes to plus infinity, minus infinity, not just along the special curves. That can be
I mean, you can attempt to answer the sort of question by varying h as well as t.
Sure.
But
I don't know.
Yeah.
Okay.
Sorry, no, we don't have a complete theory of all metrics. Scalar curvature of all metrics.
I mean, you said there's some Hopf-Riemann theorem, right? For metrics, for the space of metrics. Is that correct?
Could you elaborate a bit more?
Well, you mentioned that you can connect any two metrics with a geodesic.
Yeah,
Is that true?
is that true? I don't. I thought. I'm not sure anymore.
I mean, locally, this seems to be fine at least, right?
Yeah.
That you get everything. But
Well,
okay, maybe I'm wrong. Yeah.
I don't even
Maybe it's
know
not
if
true.
it's obvious locally.
No, yes, true. It's just a finite dimensional intuition, but maybe
Hmm.
that's true.
Yeah,
There's
that's
somehow a
very
pointwise
far.
question that the smoothness doesn't look too good if you have multiplicity.
Yeah, I suppose that's true. Yeah, that's a good point. It might be sensible to work that out. Exactly how much of M are we hitting with this
Oh,
with
so
this thing?
you can't even do this locally, so then you don't understand the local behavior near a given metric. There's a certain subset that you can reach with these Ebin geodesics. That would be bad.
Yeah. Hopefully that's not exactly what's happening. I guess we'll have to look into that.
I don't know. I haven't thought about it.
All right. There's no other questions. Thanks, Tim, for an interesting talk.
Thanks very much, guys. It was good to see you all.
Thank you.